So our paper titled Automated Vision-Based Bolt Handling for Industrial Applications using a 6 degree of freedom manipulator. So our presentation goes like this, start with introduction, and I'm going to show some related work who are contributed decently in this field, and our contributions, and our experimental setup and methodology. And at the end, the results, what we have got and the observations we have got, and ends with conclusions and our future directions in this field. So coming to the introduction part, in industrial automation, the main aspect is how efficiently we are manipulating an object of our interest. So especially when this, it will start from the global camera, which is fixed in the experimental setup, and its field of view covers the bin and as well as the place where we are going to place our bolt for the size estimation. And initially, the global camera will capture the RGBD image and it will extract its point cloud. From on that, we will apply the k-means clustering, where the k-means clustering will cluster the total captured scene into 3 clusters: bin, bolt, and table. And after that, our object of interest is only the bolts. We will eliminate all the other clusters except bolt. And after that, grayscale conversion of that segmented image and binary threshold will be applied to that area of interest. And after that, the main important aspect is the search volume extraction. So if we do this perfectly, that we will definitely reduce the computational burden that is going to be happen to search everything in the detected volume. So the data conditioning is carried out to reduce the search volume. This helps obviously in computational efficiency and speed of the algorithm. The first contour identified and minimum area rectangle will be drawn on the contour as a bounding box. And voxel grid downsampling is applied on PCD to reduce the computational complexity. And now our template, which was imported from the Autodesk, now will be moved to the objects PCD. So the center of templated is translated to the position J of the object PCD. So which is denoted as P subscript J, S. So now the template will be rotated from 0 to 360 degrees for both yaw and pitch angles. So for every combination, so we are going to store our chamfer distance as shown here as a equation number 1. After that, the minimum distance will be stored at one point of time. The template will completely, or else we can say maximum matching will happen. So we will store that data as a feature vector here as shown in equation number 3. So which is in now it is in image coordinates, so pixel coordinates, and the capital Z actually in real coordinates, which is getting from the depth camera, direct depth camera. So using projective transformations, we are going to localize that bolt, which is in image coordinates, to our Cartesian coordinates in the frame of camera. And after that, using projective transformations, we have transformed this X and Y coordinates, which subscripted as P, which are in image coordinates, will be converted to the real world coordinates. Now the final feature vector will be capital P, theta, delta. Here, theta, delta are yaw angle and pitch angle. So definitely these yaw and pitch angle needed when the bolts are in overlapping configurations. So on flat configurations, only the yaw angle will work. But in case of overlapping configurations, we need the pitch angle also. So now our feature vector is in the frame of camera. So that should be transformed to the robot base frame. So essentially this equation number 6 will do that. So the feature vector which is localized, or else the bolt which is localized respect to the camera frame will be transformed to the robot base frame. So after that, that feature vector will be given to the move it interface. So here we are using RAS1 and Gazebo for our simulation. So the move it will do the pick and place operation. So now we have localized the bolt and we have extracted the features and as well as their orientation, essentially yaw and pitch angle. So now robot arm will pick that bolt and it will kept under the global camera. So where our next process will come into the picture, which is size estimation. So size estimation and sorting here. So we, for example, we like a T shape, a bolt will be in T shape. So we will find out its centroid and we will draw a perpendicular line from its centroid to the boundary pixel. So now we will get the radius. So we will multiply that radius with the 2. Again, this size subscripts P in image coordinates. So definitely that width will be in image coordinates. So that will be converted to the real world coordinates using our depth, which we will get from a kinetic depth camera using equation number 8 and 9. So at end we have localized and as well as we have the size estimated the size of the bolt also. Our next task is to sort them according to their size. So for that we have set up a heuristic approach after doing a lot of trial and error experiments. So we set a heuristic criteria for sorting the bolts. So for example, for M6 bolt, the diameter of the bolt will be 6 millimeters. So if that falls under in between these boundaries from 5.5 mm to the 6.99, so that will be considered as M6. So obviously we will apply same criteria for all other sizes also. It is our Kinova Gen 3 light, and here, okay, it is a Intel RealSense 2, but in simulation we have used a Kinect camera. So it is a bolt, and I will show the video at the end. Yes, so these are all the results and observations that we have got. So here, this is the error in meter. So here all quantities are in meters only. So this is the position error. So the observation from this, and these are all the size estimations. It should be 6 mm and we have detected as a 5.9. So the corresponding errors are there in millimeter now. So this is our RMS error. And these are all the trials. Like in each trial, we have got the classification without any mishaps. And these are our observations. So coming to the position error, like we have got a root mean square error as 0.05 mm. So this error maybe depends on the steps of PCD points considered during the template matching. And additionally, ignoring the scale of the template, we can also contribute to the error, though it is insignificant. By addressing these two factors, the error can be further reduced, but at the cost of computational time. So the experiment was conducted in the same setup for repeatability and reproducibility. And the size estimation algorithm performs well, achieving 0.36 mm, which is very less. Size estimation depends on camera intrinsic parameters also. And it was observed that error can be decreases with high resolution. But again, it is at the cost of computational time. The discrete nature of these pixels might force an error in estimation of the distance. I told you whatever the perpendicular line that we have drawn, that will be affected by this discrete nature of the pixels. Like if you improve the nature of the pixels, definitely we will get the more straight line, which is exactly perpendicular. Definitely we will get the less error as comparing now. And this research presents a novel method for industrial component handling. So combining RGBD camera data with our pose estimation pipeline. And these can be accelerated using our GPU and as geometric descriptors, and expand the system's capability to handle diverse components to integrate with the dual arm robotic system, exploring deep learning techniques to overcome the limitations of template matching. So in our future work, we want to combine, like we want to go with a hybrid approach. So in initial stage, we will use the deep learning to detect, and after that, we will bring the template matching to refine our results more. And this framework, like for experiment, we have used the bolts, but we have generalized this framework. So instead of a bolt template,